Hello, this is Max Drake. I'd just like to talk about this Y2K38 or year 2038 problem with the Unix time. Supposedly, well, not supposedly, on the 1407 AM on Tuesday, the 19th of January 2030, any computer or device clock running a 32-bit Unix time will reset to December the 13th, 1901. So I first want to talk about the Y2K challenge and the issues with that. So the Y2K, which is the year 2000, when that was coming around, there was a slight glitch there where programmers had actually used 2 days for the day, 2 days for the month, and 2 days for the year. So the year went as 97, 98, 99, 00. Because there was an implied, well, it wasn't implied, it would have been coding in as 1997, 1998, 1999, it would have rounded back to 1900. So therefore the time would have gone backward. So that was because they were using 2 digits for the year instead of the 4 digits. So if it's got 1997 and it's 4 digits, 1998, 1999, it will then round up to 2000. So the issue why that happened was a lot of the computer programmers were actually working on very small memory to actually write code. Now, if we look at the size of the RAM, which is the RAM is a random access memory that we got size. So RAM on your computer or on your phone is, it takes from the hard drive or your solid state hard drive, and it pulls it into random access memory, and that's when it can run the program. So it needs to be in random access memory. Now, if you look at a mobile phone nowadays, and I've just got my wee mobile phone here, with little Android one, they normally come in with about 1 or 2 gigabytes of RAM. So that is one with 9 zeros after it. So a billion or 1,000,000,000 bytes. Now, in the old days, they would only be playing around with something like 128 kilobytes or 128,000 bytes. So it's about 0.0013% of what a phone has nowadays. Now, that's your RAM. It's not even your hard drive. So that's actually what you'd need to pull up. So they'll have to write very, very efficient code. So that's why they were abbreviating the time down to 2 digits instead of 4. So that was a sort of logic behind. Tend to forget those sorts of things. So if we look at that, so what is a byte and what is a bit? So we got all these giggly bits at the moment. So a bit is atomic. It's the smallest unit of storage. So we can store either a 0 or a 1. So binary. So it can be use the binary, which is 0 or 1. So in a computer, it's all zeros or ones, bits. So anything with 2 separate states can store 1 bit. So it can either be 1 or the 0 or the 1. And if you group 8 bits together, you make 1 byte. So here we are, the giggly bytes up here. So 1,000,000,000 bytes. So here we can make 1 byte. So we need 8 bits. So if we look at 8 bits, there's 0, 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So 0, 1, 0, 1, 1, 0, 1, 0. Or it could be here, 8 zeros. So that is 1 byte. Now, 1 byte can store about 1 character. So an ASCII character, an A or an X or a $sign would fit into there. So if we look at 32 bits, it's basically 8, 8, 8 and 8, and it all adds up. Now, when we actually look at a signed 32-bit, a signed 32-bit means that the very last bit is actually used. It's still only a 1 or a 0, but if it's a 0, it represents a plus number. If it's a 1, it represents a negative number. So here you can see it's at 0. So this is a little GIF happening here. If it's a 0 here, you can see that's a positive number. Now, when it rolls over to a 1, it converts into a negative number. So the decimal goes to negative. So a 32-bit to the 31 power, that means to all of those, less that very last number there, or very last bit there, 2 to the 31 goes to minus 2,147,483,648 digits that it can actually go through, and then it can go to plus that, minus that. So therefore, and 0 is in the middle. So it would go from minus and then count all the way up to there. So when it goes into the negative, it jumps back to 1901. The month is 12 and the date is 13. And when we actually adjust on the very end there, in 2038, in the first month, that's when it reaches 0, 1, 1, 1, or 1 all the way back through to the 31 through there. So as soon as we hit that 1, we go into the negative. So that's a bit of an oopsie if we suddenly go back in time, because they can mess up a whole lot of clocks since they're actually working in real time trying to go forward. So the Unix time was based as 0 when it was when we'd actually got the time in the middle at 0, as in all of these bits ended up not at minus 2 billion, but at 0, was the 1st of January 1970. And therefore, the last time we can be stored with a signed 32-bit is on the 3:14 a.m. on Tuesday, the 19th of January 2038. Now, this is when it's counting through as a second. So as every second ticks away, the value keeps increasing, and it will eventually reach the maximum number that it can get to. So if we just go into here and we look at the epoch converter through here, and we just go to the home, when it thinks about it through here on the home, it'll tell you what the actual time is there. So we use a single number, and it's just an integer number that will actually count as time. Now we can use a converter to convert that into a year, a month, a day, an hour, a minute, and a second, because we are actually counting seconds through this number here. And this number here, at this point here, represents the time Tuesday the 22nd of September 2020 at 3:18 GMT, Greenwich Mean Time. So this is my time plus 12 hours. It's the 22nd of September at 3:18 p.m. in New Zealand here. So from this one number, we can calculate all of this. We can then describe it in this fashion here, either for GMT or in our local time all the way through. So having this single digit number is really brilliant. But this is when it comes to a stop and rotates over, rolls back to the time of 1901, when this tricks over to this point in here. Now, there are ways that we could do this. If we take this signed number, so this very last digit, instead of representing a plus or a minus, we take that as just being another non-signed, unsigned. We can then go through and go from 0 through to 4,294,967,295. So this is 2 to the power of 32 minus 1. So this says if we set our 0 at the 1st of January 1970 and count forward, we are not going to run out on an unsigned 32-bit number until 2106. So if we actually have a computer, we can actually just go in and program through and make the signed 32-bit integer into a 32-bit unsigned bit. But to do that, we'd need to get into the kernel. Now, the kernel is the bit that talks between the hardware and the software. So we're writing code in Python or things, or we're writing stuff that comes through and we can see as ASCII text, which is a number, comes through as our letters coming through onto our screen here. So that's human readable. Then has to get translated into binary right down on the hardware stage. Now, the kernel part of things are usually in your software system. So the Apple Mac software does this, and they use the epoch time, but they start from January the 1st, 1904. Now, you can see when we go into the negative, we will actually go into the negative that goes 1901. So 1904 is after the 1901. So it's actually using the negative to actually use this starting frame for that's the Mac OS system using the 32-bit. The Unix and the Linux systems consider the epoch time as starting from the 1st of January, and I think also Android do as well. I'll talk about my phone. So if I look at my phone, and I'm just looking at my mobile phone here, and I've just done a screenshot where I've gone and I've taken my time and date off automatic, and I've tried to set the time, and I'll only allow to set it up to 2037. It won't let me set up a year after that, and it will let me go back to 1970. It won't let me go back prior to 1970 to set a date prior to that. So therefore one can assume that my mobile phone, although it has 4 gigabytes of RAM, can only is only a 32-bit timer on there, and it's most probably a 32-bit processor as well. So therefore everything all the time is based on that. So therefore after my phone will be no good after 2037, because it's basically on a assigned 32-bit card that it's using to actually count the time on it. So basically it's saying after that time it's going to reset to 1901 and it'll brick itself. So that won't work with anything else if it tries to coordinate time with anything else, because it can't do it after that period. So that's what happens with this. So one way is that we modify it, and then we can go through and we can get another year. So from 1970, when it started off as being 0, to so when we started off of the 1st of January 70 through to 2038, so 70 to 2000 is 30, so that's basically 40, so it's 70 years. So this is giving us another 40 years plus 2038, so this is where we get in the 2106. So that's where that number's coming. So we're just adding we're taking the 40 years prior to this, and we're adding it on to the end of the other one through there of 38 years, etc. So that's what it is doing. So the Apple does that, the Unix does that, and the Linux does that. So what do? Well, first of all, now they know that it's coming up. A lot of things are starting to move into the 64-bit. So the issue which they actually had back in 2000 Y2K was, in fact, that they were writing programs in the 1970s and the 1980s, and a lot of those they didn't have much memory. But as they got into the 1990s, so that the computers got bigger, and so they could actually write the 4 digits in there. But the thing was that a lot of their programs were sitting on top of legacy stuff that was running still in this. So it's an old code on old machines that were doing this. So they needed, but the other ones were built on top. So this was at the very, so it was like the foundations were on this. So as soon as you took the foundations away, the other ones fell down too. So this is what they actually had to go and fix. So this is the issue that we got here. So some of the solutions is that we can actually readjust this so that they start from 0 from 2007, and anyway we go to the 32-bit rather than the 30 signed, and we can then move forward. So we move the problem out to 2006. The other thing that we can do is that we can go into the 64-bit time. So if we just look at the age of computers, in the early 70s and coming on through, we started to get the first 8-bit CPUs. So these were basically desktop computers. For that, you had mainframes and all the rest of the stuff. So the big mainframe stuff, the IBMs, the Unixes, and all of those. Then you start to get the 16-bit CPUs, and then you start to get the X386. So I'm just going to go through the 386 type things coming through here. So the X86. So the 16-bit ones started to come through in the late 70s. So those were the 16-bit. So that was a doubling of the 8-bit. The 32-bit computers started to come in. So the 386s and stuff like that started to come through about mid-80s. So from the mid-80s through, there was basically 32-bit stuff, all the chips coming through were doing those. And the 64-bit started in early 2000s, in 2003, in fact, in those points. So a lot of the stuff, so 64 bits So they basically got 15 years before the 64 bits coming through. But it's 2020 and we're still on 64-bit. And I started only buying my 64-bit stuff about 10 years ago, so about 2010. So there's an awful lot of 32 bits that have been around for about 25 years prior to moving over to 64 bits. Now, if we go to 64 bits, it's basically your 32 bits through there and then another 32 bits on top of there. Now, when you start looking at the dates through there, this is where we are looking at the 2000 or even the 4000. So this is where we are here, and we can get numbers through to here. So basically, if you counted this in seconds, this is apparently 20 times after the end of the universe, and so we won't have any problems with the time running out in the 64-bit information. As such, if you are counting seconds, which is what we've been doing from the 1st of January 19 with the signed 30-bit, we've been counting a second every time. So that's how they're setting the time. So the Mac considers its epoch time counting every second as we go. The Unix and Linux systems are counting epoch time from the 1st of the 1st 1970 every second. And that's when it's going to run out on 2038. Now, Microsoft Windows considers its epoch time starting at the 1st of January 1601. It's based on 64 bits, so we can go an awful long way. But what they do is that they use 100 nanoseconds. Now, 1 nanosecond is 1 billionth of a second. So that's 1 divided by 1 with 9 zeros under. So it's a very, very small increment. It doesn't. It's 10 billion millionths of a second. So it's 1 with 7 zeros after it. So it's counting. So their problem is going to come up in the year 2184. So that's the problem through there. So with this fact that from now forward, or from 10 years back or whatever, they've started to convert the time, and instead of counting the time in 32 bits, they're counting the time in 64 bits. So a lot of them were the later programs, both in Unix and Linux and in Apple for the later programs, which are in the 64-bit, they're counting time in 64-bit, their things. As long as they're not running on software that's running 32 bits underneath, because those ones, if you're running a bit of 64-bit stuff on top of a bit of 32-bit, and 32-bit runs out, so the 64-bit falls over. So again, we've ended up with the same sort of issues. Now, where this occurs is when we start talking about embedded devices and stuff like that. So if we talk about embedded device, this isn't an embedded device, but basically it's a modular piece of a device. Now, this is a Raspberry Pi. This one here is based on an earlier one, so it's a 32-bit. The latest Raspberry Pi is a 64-bit, but the earlier ones doesn't. But it's basically plug and play. You don't actually go and build a specific unit for a specific thing. You go and find a generic timer bit, which is most probably a 32-bit something, and you plug it in, and that's your little timer thing. So a lot of embedded devices might actually be very small modules, and then they'll be sealed totally in plastic, so you can't go in and redo them. Now, they may have input and output points that you can actually go through, and they're usually for receiving or triggering information, and you may not be able to pre-program for them, so that the actual software code is already embedded in there. Now, the software code to actually talk to the hardware, to change the hardware to think, instead of a 32-bit sign, to make it an unsigned one, you have to go and rewrite that. Now, that happens at the kernel level. So that happens at the point where we take our human readable stuff, like we can see on here and all the screens, and it goes down and talks to the actual hardware. So we've actually got to go, and the kernel is the interface between talking between the software and talking between the hardware. So we actually have to get down to that kernel. So that's happening in the operating system level. So you can actually have modular systems, but a lot of them are actually totally integrated as one big mass. So as the Mac one, because it's proprietary, they've locked their stuff, the Windows have locked their stuff up. Linux is open, and you can actually go in and maybe do some bits and stuff. On this particular one here, this is has got a little card. You can actually put a card into here, and you can run Linux Ubuntu onto it, which I think it comes with automatically and things like that. But I've also run Microsoft Windows IoT software, so that's the operating system that runs on that. So I'm not too sure if that's a 64-bit timer or a 32-bit timer on that one, but that's what actually happens through there. So a lot of them are actually modular things, and a lot of them are actually all encapsulated, and so they are basically in embedded devices. So you've got things which are already set up. They've actually just said, we're not running on those systems. We've got something embedded that's actually just doing our counting inside there. So we can talk about a cloud storage side. So I've got a Western whatever it is, which is storing all my cloud. So that's basically got lots of things. You've got things like pumps, hard drive, TVs, cameras and stuff like that have got timing. My camera, if you take a photo, on there you can put today's date and today's time, so you can set that. So it's an older camera, so it's most probably 32-bit and taking that. So after a certain time, that will roll back over into 1901. Now, it just means you might not have the date function, or it might actually break the camera completely and say, I need that to actually run. GPS receivers. Now, this is when it's receiving these, and they're receiving that data. They've got a timer in there themselves, so that could be based on things. Game consoles, microwave ovens. If your microwave dies, it'll be just toss it, and actually, will it last until 2038? The thing is that they actually have embedded devices in them, so they got these modular components that they've all locked in there. They've gelled them all up, and they said that's where they go. Can I go in there and reprogram that 32-bit signed into a 32-bit non-signed? Most probably not. And is it that important for a microwave oven? My phone. Now, my phone at the moment, since it's got software in there, but I don't know whether I can get right down at the hardware on here to actually program it. Now, since phones usually last 2 or 3 years, it most probably be, it's not going to last until 2038, so maybe that's not particularly critical anyway, because you'd replace it because it's a really useful thing. Now, the ABS braking on your car and the airbags on your car, they also have embedded devices. Now, whether they're actually doing real-time stuff, so this is when you've got things, and I just really want to go through to this part and get these notions and ideas across. With real-time systems, is that you've got using real time to actually get some information on there. So an example I'm going to use is an Internet of Things one, which is a live temperature reading of a refrigeration truck or van taking chilled frozen food across the country. So you've got sensors inside there monitoring to see that the temperature inside the chiller is actually between certain set points. And if it goes over set points, you can acknowledge those set points, or you can actually have something which will actually send a different signal. But you could actually just have a little box that would actually take those sensors, and you drive the truck from Wellington to Auckland, and it just takes those readings. Now, if it goes over its minimum set point or maximum set point or whatever, when you get to Auckland, you can say, oh, well, look, it went over the set point for 4 hours or 3 hours or something like that. There's no way you can actually go through and do any intervention inside that. You've just registered the fact that that went over temperature. But in fact, with a lot of IoT devices, you can actually have this real time sending the information through a LAN, through radio masts and things like that, with Sigfox and low Ra WAN, which will actually embed you where it starts send packet of information through that will be sent back to a console thing, so that you can see in real time those things happening. Not quite real time. There might be some differences depending on when they can connect to the next cell tower. But you can get packets of information such that you've got time enough to do an intervention, such that if it goes through one lower set point, it gets to the point where you can do something before it gets to a critical set point, such that something might spoil, so that you can do interventions into those sorts of areas. So That's one of the things you can do. Another one is the utilities. So if you've got a council that's monitoring traffic lights or things like that, those will have embedded devices in, and they're most probably running on a real-time clock that is actually saying this is what time of day it is. So, at certain times they have heavier loads of traffic, so they slowed side roads down to let the main roads run a little bit harder. So those ones have potential things for that. You can have flows in pipes. Now, the flow in the pipe needs to most probably have a real time next to it so that you can actually say, we need to throttle that back, so that you can send some information to an actuator on a valve to say, close that down for 10 milliseconds and then open it up again. Now that's a counter. You can count 10 milliseconds. You're not worried about those ones because all those embedded devices are doing is just doing a counter. So they could be 8-bit, 16-bit or whatever, but they're not calculating real time. You want something that's actually having your date and time, that's actually saying, I need this date and time to actually relate as to what's actually happening in real time. But something actually activating and deactivating can actually just run on a different counter to what you actually need. So those ones don't necessarily need to any replacements. It's the ones that's doing the real time counting. Now that could be back at a control panel, or it could be a control actuator that's running a whole lot of things. And the example I use with that is something like a security system in the building. You have a swipe card access. Now, when you actually swipe the card at the door, there's a mag lock on the inside that is actually you're going to set to release. But it's taken the ID off the card that needs to go back to a database to say that it's a registered user that has a priority that they can actually go through that door at a specific time, if it's after hours or something like that. You may be a cleaner, or you may be somebody who they only let access into that building via other doors, not necessarily that one, so that they can pass a security person. This one might be somebody who has a hire realtor. So it's got to go to a database and actually read that card ID off and say, yes, whoever has that card has the authorization to actually go through that door at that time. So they will then release the lock. That one goes back to most probably a computer because it's got a database in it that it's got to go and do a lookup. That one most probably has a 64, that was most probably the software has been updated so that it's running on a 64-bit clock instead of a 32-bit clock, or a 32-bit clock that's unsigned. So that's quite good. So a lot of the actual, like with maglocks with a window alarm, like if you've got something and somebody breaks into a window, so they open the window, the switch triggers to say that that window's opened after hours. It sends a signal back to a control panel somewhere saying, I'm open and I shouldn't be. And it says, at this time of the night, you shouldn't be. And so it's got a bit of logic into that. That will then date stamp at that point time there. So that the actual read switch on the window doesn't need to know the time. All it needs to do is send a signal when something happens. Security cameras, on the other hand, would need to, because you see a security camera a lot of times, like if you take a still photo, inside the metadata of the picture is the time when the picture's taken. So therefore, on a security camera, you also want inside the security camera that date time to make sure that you've actually got a record of when that actual event happened in real time. So those ones will have a real-time reader. So if that's 32 bits, again, that's going to drop over. So those security cameras will need to be replaced by that time. Now, why am I talking about this now? For things like buildings, it's not going to happen for another 18 years. But a lot of the times, those software, you're not necessarily, if the software is not broken, why would you bother replacing them? But you want to suddenly saying, oh, well, we're looking to refurbish the building in 10 years so that we can just start making plans that those sorts of things are replaced and actually upgraded to make sure that they're actually appropriate for when the time happens. So the thing is, if you're doing a new security system in the next year or two that's most probably going to last for another 20 or 30 years, maybe you've got to start considering these things now and suddenly saying, well, no, we actually want to make sure that we've got a 64-bit counter instead of a 32-bit counter, or if you've got a 32-bit counter, that it's actually going to be running, that it's unsigned, so that we've got all of the information to do that. Again, the HVA systems and things like boilers and stuff like that. It's like paint systems in New Zealand. We say, paint system's only good for 10, 15 years. In fact, most people we'll push them to 20 years or something like that. New Zealand is not that good, and a lot of other places are not that good at maintaining something. If something ain't broken, why bother replacing it? But if you are looking forward to things being replaced, you don't want to end up leaving something which is going to give you vulnerabilities. So, in fact, it's worth planning ahead for these sorts of things. Again, in hospitals, you've got things which, and these may not be critical, they may just cause a bit of disruption that causes a bit of downtime, and but it could be something that your tenants, it really disrupts your tenants and does a whole lot of things that you just want to make sure that if you've got a process of upgrading or replacing, that these things are actually just planned for at the time. Hospitals, you've got critical dosing stuff, and if that's based on a time base and it's based on real time because it registers a whole lot of things, that could actually kill someone. So you actually want to make sure anything that happens, and again, you want to start replacing and doing this now. You don't want to end up doing something in a mad rush at the very end. And at defence, there's critical equipment there and things like rocket launchers and the stuff. If they're on real times and stuff, those can actually happen. Airplanes as well. There might be some very low grade thing that's actually just taken the time and it's counting the time, but it's counting it in relation to real time for things like pump valves and stuff. An example that I'd use as well is petrol pumps. When you actually go to a petrol pump, and if you use a card at the petrol pump and things like that, it's giving you a date. So the pump's actually giving you the date and the time that you actually did that at that point in time. Now, if that's a 32-bit one and it stops and it resets it back to 1901, there might be something within its own logic that's suddenly saying, well, no, that date is not today, and start shutting down. So that could cause a whole lot of disruption and stuff like that. So it's sort of like, if you're going through and replacing stuff, to be planning for those things as well. Now, an example of this is, one of the things which is a suggestion is that we go, this one here, where we just change it from a signed to an unsigned. This one, we are not replacing anything. All we're doing is programming down at the kernel to actually just put another bit on the end of our thing to actually make it go from 1970 forward, such that it goes to 2106. But if you go into trying to put a 64-bit of information onto a program or onto an embedded device that is based on a 32-bit structure, you'll get an overflow and it will just crash. And the example of this is the Ariane 5 rocket, which blew up on the 4th of June 1996. And this was when they ended up with an overflow in a component that would only take one size bit, and it was overflowed. More data came in, so it was an 8 bit, 16 bits were trying to be put in, and it just crashed. It kind of said, I can't handle this, and it just reset itself. And what it actually caused that to happen, so something so very small triggered all these other consequences after, that ended up resulting in a self-destruct command being set to the vehicle, and it blew up. And so there was billions of dollars damages from a coding error. So it's an interesting thing coming up, and I just wanted to do a little bit of research on that, and I was quite fascinated by what it is. From the point of view of facilities management, 18 years is not that far ahead. So you've got systems in place which are not only your security, your whole lighting, your electrical, your data, a whole lot of stuff could be being, you've got newer stuff sitting on or piggybacking over the top of older stuff, that if you're going to be doing replacements, refurbishments, those sorts of things with the buildings, within a certain period of time, those can be planned so that you can actually make sure you remove those obsolescent things and replacement with newer ones to make sure that you're not going to get those failures actually happening. Or if those buildings, or you have no plans to actually replace those things past that date, for maybe the replacement times within 2048 or something, that you actually go through and have those things checked. And if you're checking at an earlier time, you've actually got time to actually place that through. You've also got time in your documentations for your brief, when you're actually updating and doing these sorts of things, to make sure that all of these things are logged in, or that you've actually got that as a criteria of the brief, that you're suddenly saying we want 64-bit information. Security cameras, if they're sitting on the outside of the building somewhere and you have no access to them, they can be quite expensive to go up and to take down and replace. So it's just things that you need to consider, and this is one that's it's quite an interesting one. Another thing that's coming through, and it's sort of a epochy type thing, which is the Y10K. So in the year 10,000, we're going to end up with 5 digits instead of 4 for the year. Now, if somebody's doing a simulation based on maybe global warming into the year, right the way through into the 10,000 or 20,000 or some other things as to tectonic shifts and things like that through, say, if you look very far into the future and then start working you back, if you've only got 4 digits for your date and you may want 5, then that could be another thing that could actually cause a bit of programming issues around. So if you're updating for one, why not update for another and actually just put a further digit on, even though it's redundant and never won't be used for a long period of time. So this was something that we suddenly said, well, Y2K, which is the year 2000, 38 years later, we're going to be confronted with the same things again. So that is now only 18 years away. And there is an awful lot of 32-bit computers out there that are still running and still doing something, especially with the embedded devices. For the computers themselves, most probably everybody by the year 2038 will be running 64 or 128-bit computers. But there's a lot of stuff that's piggybacking on, and that was what a couple of things which are watching some information on the Y2K was quite interesting. One, when the actual event occurred, they'd put so much resources in, billions of resources in, to make sure that this wasn't going to be a problem. So one, the redundant stuff was actually cleared out to make sure that all the new stuff was brought in. So that was actually quite good of actually just making sure there was a set point where things were actually updated by. The other thing that actually happened is that they actually had scenarios in place as if something did fall down, that they had a fallback position to go to. Now, where that was quite an interesting one is in the 9/11 attacks on the World Trade Center and all of those. The Wall Street opened very shortly afterwards because they had actually got scenarios in place for if a big crash had actually happened because of the Y2K bug. So, in fact, anticipating and planning for some of these things allowed for extra things so that fallback positions were actually made for some of these things not happening. So the airplanes didn't fall out of the sky in the Y2K, but we are becoming a lot more intermeshed with a whole lot of things nowadays. And so thinking about this at this point in time, being able to plan for them coming through in the future is not a bad thing to consider, especially if you've got things like assets and buildings which are coming through. If your microwave oven fails, so what? There's some of these things. If your camera gets bricked, so what? Well, it's a bit of a pain because, but if it's one that you've got now or you've got something coming forward, if your TV's bricked, depending on the replacement stuff and things like that for stuff, a lot of these things, because of the their electronic nature, a lot of them won't last, a lot of those things. But it's worth considering the fact that when you're going through for the next purchases and things like that, that you've actually planned for that. Anyway, I hope that's been of interest to you. I found just doing a little bit of research on that quite fun. I found this GIF by Monakiko, a fantastic thing, which is on the Wikipedia one through here, and I did use that one and just cited the fact that it is open domain. There is another one which actually shows the problem, and it just highlights when that failure actually occurs through there. I've actually just written an article on it and gone through some of the issues coming through there. There are a few interesting videos on about it. This one was done in 2013, talking about this stuff. This particular video, I'll give links to both of these ones, talks very well about the Y2K and what was actually done. It was sort of a bit poo-pooed at the end, but there was an awful lot of work and things did happen behind the scenes. And this one's actually a very interesting one, just about time managing. So that was just something that I just wanted to demonstrate, was the figures of times and how they're represented. We can use that number and represent that. So we can convert that through to that with a bit of coding. So the epoch converter here has a whole lot of codes as to how to use JavaScript to take this number to make these sorts of representations through there. And it is quite handy, depending on what program you're doing, as to how you can actually make those descriptive things. Sometimes it can be quite hard. It's just the way that it's doing. So thank you very much for watching. If you found it useful, can you please give a thumbs up? Otherwise, I'll pan your heart. Thank you.